This is 15.7, and we're talking about polyprotic acids. After this lesson, you'll be able to make qualitative, meaning you don't have to do any calculations, predictions about the behavior of a polyprotic acid. So first of all, just what does polyprotic mean? So poly means many, and protic, that's referring to protons. So it's saying many protons. We can have monoprotic, we can have diprotic, and we can have triprotic. It doesn't go above that. We're not going to get 4. So the polyprotic is specifically referring to the di and triprotic, not the mono. So here's some examples. We've got a triprotic here with the H3. The other two are diprotic 2. It's saying there are 2 protons that are labile that can be released. So looking at these examples I have, are they weak or strong? Are polyprotic acids weak or strong acids? They are weak, except for sulfuric, which is, of course, the H2SO4. And hopefully you would memorize that that is strong. It also means, however, that only the first hydrogen is strong. They're not both, only the first one. So when you have the polyprotic acids, labile protons are removed one at a time from an acid. So each proton has its own K value. So for example, this is phosphoric, this is triprotic, H3PO4. So it's like there's 3 stages of hydrogens being removed, 3 stages of the acidic hydrogen leaving, and each one has its own K value, Ka1, Ka2, Ka3. So you can look at these and see like how are they different, what's going on, to see the progression of the hydrogen being released. So as the negative charge on the particle gets higher, meaning the negative charge on the conjugate base over here, as this gets harder, here it's -1, here it's -2, here it's -3. That gets higher, it gets harder and harder to remove another proton, to remove another positive charge from something that's already negative. So knowing that it's going to get harder to remove successive protons, put the Ka values in order from largest to smallest. So that is, I want to fill in 1, 2, and 3 in these subscripts over here. I want to say which K value is the biggest one, Ka1, Ka2, or Ka3. Well, if it's going to get harder and harder to remove another proton, then that means the Ka values are going to get lower and lower. So this is Ka1 is the biggest, then Ka2, and then Ka3. The strongest acid out of these 3 chemicals is H3PO4. HPO4 2- is the weakest. When we put H2CO3, carbonic acid, in water, let's try to put the species in order from highest to lowest concentrations. And I've created some text boxes off to the side that we can just slide into place. So what I'm trying to say is, here's the diprotic acid. Here's the series of acid dissociation reactions. I want to try to figure out of these 4 chemicals over here, which one has the highest concentration, which one has the lowest concentration in solution. So it's like initially, if I put this chemical right here into solution, what will the relative concentrations of everything end up being? Well, Ka1 is bigger than Ka2, but remember, it's still weak. So this number is still less than 1. It's still saying that we're going to have more of this chemical than either of the other 2. That's how weak acids work. So the highest concentration is going to be the H2CO3. We'll have the most of that. Now, when that dissociates, initially it's going to make equal amounts of H plus and HCO3-. They'll be less than the concentration of H2CO3, but initially they start out being exactly the same. So for now, let's just drag them over there together. This and this. I'm saying those start out as being the same concentration. But then look what happens. The HCO3-, some of that's going to dissociate. So some of that will dissociate and go away in order to form more H+. So that means that the concentration of H+ will in the end be bigger. And I'm not sure if I'm going to be able to move this because it's driving me crazy. Here we go. Let's try again. All right. So in the end, the H plus is going to be higher than the HCO3 minus. And then last in line, of course, would be the CO3 minus 2. So that's putting them in concentration, putting them in order from highest to lowest. I would say that that right there is the most common question I see in relation to polyprotic. So usually the pH of the polyprotic is really just controlled by Ka1. It's that dissociation that matters. That stage 1 dissociation controls the pH of the overall solution. The Ka of the second stage is smaller, and in addition to that, the presence of H plus from the first stage suppresses ionization in the second stage. It's another example of the common ion effect. Essentially, you've created some of this. So when you start looking at this equilibrium, you're not saying I'm just putting HCO3 minus out there and watching it dissociate. You're putting some HCO3 minus and some H plus in there simultaneously. So having the H plus present is driving the equilibrium towards the left. It basically makes it so that it's less likely to dissociate. You never have to do the calculations to calculate the pH of any of these situations. It's just, if you did, what you would probably do is just look at that first Ka, that first reaction, and that's it. You wouldn't even bother with the second. Now remember, sulfuric acid's unique. It's diprotic, but it's the only one where the first labile hydrogen is completely dissociated. It's strong, and the second one is weak. So that means that this first stage, my Ka1 is much, much greater than 1. It's a number that we don't even ever look up or need because there's no real equilibrium there. We're saying it goes to completion. So in all honesty, I should not make this a double arrow. I should make that a single arrow. And then here, this one's weak. So now your Ka2 is less than 1. If we look at the titration of a diprotic acid, you basically, just like one hydrogen is being released at a time, you also titrate one hydrogen at a time. So when you add a small amount of base, that hydroxide is going to remove H plus from the H2A first. It's basically going to do this. This is an acid-base neutralization. This is not equilibrium. And it's not until all of the H2A has been converted into HA minus that that species starts to be neutralized. So after you neutralize all of the H2A, then you start on the second stage of neutralization. Now, if you take those two neutralization reactions and add them together, that's going to give you the overall neutralization reaction. And this overall reaction is what we would normally write if I was asking you to show me overall an acid-base neutralization reaction for a diprotic. This is what we would write. This is how we wrote it last year. This is how, well, it was not net ionic last year, but this is how we wrote it back in chapter 4 as well. And then lastly, a titration curve for diprotic acid. What you need to notice on here is there's basically like two vertical sections. This is like taking two titration curves and putting them together. If it was triprotic, you'd see 3. So I've got the different parts labeled here. We've got initially down here at the bottom, we have our first half equivalence, we have our first equivalence point. Then we have our second half equivalence and our second equivalence point. So if it was triprotic, we'd have yet a third equivalence point. And the true neutralization point for this acid is not until you get to the second equivalence point. Again, you're never going to have to label all of this. You're never going to have to calculate any of this. What I think you should recognize is that if it's diprotic, it's basically 2 titration curves put together. If it's tri, it's going to be 3 titration curves put together, and that you haven't actually neutralized it until you've gotten to this point up here. That's where the neutralization actually occurs, is at that second equivalence point. And there's no practice or anything else with this one.